Our next speaker is Daniel Robbins.
Okay, yeah. Thank you for having me speak here. So I was a postdoc here from 2006 to 2009 in the Weinberg theory group. I never worked with Stephen, but I really cherish and was honored by the interactions I did get to have with him. He's definitely one of my intellectual heroes. And as we've learned in this workshop, he's also, besides being just one of the greatest scientists of his generation, he's also one of the most quotable. And so it was very easy for me to find a quote, even a quote that hadn't been used already this workshop, to go with my talk. So this is from an article in American Scientist from 1977. He says, "Nothing in physics seems so hopeful to me as the idea that it is possible for a theory to have a very high degree of symmetry, which is hidden from us in ordinary life." So of course, the context here was a discussion of spontaneous symmetry breaking and the electroweak theory, a characteristically beautiful, popular science level explanation of it that was really lovely. But I think it also applies to the stuff I'm going to be telling you about today. So here's an overview. I'm going to try to quickly review generalized symmetries. I'm a little nervous about that with Nadi in the audience because I learned most of what I know about it from his papers and talks early on. And where I want to go towards is the idea of these non-invertible symmetries. How do you gauge them? And I want to be, following Stephen's example, I want to be very systematic and explicit if I can. So unfortunately, not following Stephen, I'm going to be pretty fast and loose with references throughout the talk, so I'm putting some up here. So I really am heavily following Gyotto, Kapustin, and Seiberg-Willett, and I'm also borrowing a lot from some papers by Bhardwaj, Tachikawa, and Chang, Lin, Shao, Wang, and Yin. And there are many, many other groups that I'm not referencing, and I apologize to those groups. Hopefully, they will forgive me. All right, so to start with, in classical physics, how do we talk about symmetries? Well, we've got a global symmetry, would be some change of coordinates that leaves the physics invariant. Emmy Noether taught us that if we have a continuous global symmetry, we can associate to it a conserved current and a conserved charge by integrating that current over, say, a spatial slice. Alternatively, if you integrate that current, let's say you're in Euclidean signature, if you integrate that current around some surface, it measures in some sense the charge inside. So when you go to quantum theory, everything gets promoted to operators. So there will be some operators U alpha M. So M here is again some codimension 1 subspace of your space-time. J is your conserved current. So if you insert this operator in a correlation function, because that current is closed, you can deform M and it won't change the value of the correlation function, as long as you don't cross any other insertions, cross any other operators. So similarly, we can show that this operator I wrote down, U alpha M, actually is a generator for the action of the symmetry. You can rewrite it. In fact, you can take any group element and basically rewrite the operator sort of schematically in this way, as your, the usual way you do over and over again in a quantum mechanics course of writing the identity as a sum over states, inserted at our manifold M in this case, but here also with an action of the group. So it's not the identity anymore, it's the action of the group. And with this perspective on it, we can write down an operator like this for any symmetry G. It doesn't have to be some part of some continuous symmetry group. It can be discrete. In fact, discrete is what I'm going to be focusing on for most of this talk. So just a few more observations about this perspective. If I take my M and wrap it around some local operator, say some sphere surrounding some point operator, if I shrink that down, and of course the surface M it's a topological operator, so I can freely shrink it down. If I shrink it all the way down to the point, I just get the action of the group on my local operator. Also, if I take two surfaces that are parallel, if you like, and bring them close together, that can also be represented by a single topological operator in this case. And if the first one was associated to an element G and the second to an element, oops, that should have been an H there, sorry about that. then when I take the limit of them coming together, I get the product GH. So in other words, I can phrase the group multiplication of my symmetry group just in terms, again, of these topological operators and how they come together inside of correlation functions. So the lesson is that for every global symmetry, you can associate a topological operator that attaches to some d-1 dimensional, i.e. codimension 1, submanifolds, where d is the space-time dimension. And now you can take basically anything that you love about symmetries, and you can translate it to this language of topological operators. You can talk about charges, selection rules, Ward identities, 't Hooft anomalies, gauging. All of these things you can now phrase in this language of topological operators. And so this raises a very natural question. Are these the only topological operators? So it turns out that no, in most theories, there are actually all sorts of topological operators floating around that you could write down. And the lesson that, so these ideas were around earlier, but I think most high energy theorists learned it from this paper by Gaiotto, Kapustin, Seiberg, and Willett in 2014. The lesson is that you can do a very useful generalization of the notion of symmetry by thinking about topological operators instead of thinking about symmetries. It contains sort of everything you had before, but introduces the possibility of some new ideas or new objects that deserve to be treated like symmetries as well. So one generalization is that you can take, rather than just codimension 1, you can take lower dimensional operators, so higher codimension. Those are going to be what we call higher form symmetries. And another generalization, which is mostly going to be my emphasis in the rest of this talk, is to take operators where when you bring them together, this fusion operation, they don't obey some group multiplication law, but something more complicated. You bring two operators together, and rather than get, the G operator and the H operator gives you the G times H operator, you get some sum of stuff. In particular, you can't just say, oh, there's an inverse operator, and when I bring it together, they just annihilate. You can't do that anymore, so you call these non-invertible symmetries. So just very quickly, I'm not really going to be using all of this, but some examples of higher form symmetries, just to give you the idea that these things really are ubiquitous. So 4D Maxwell theory has one form symmetries, electric and magnetic. So ordinary symmetries are now called zero form symmetries, and the natural charged operators under them are point operators. So if I have one form symmetries, the natural charged operators are line operators. Wilson and 't Hooft lines in this first example. If you've got a non-abelian gauge theory, you get a center one form symmetry as well. Another kind of, in some sense trivial, but also maybe not entirely trivial idea that I've worked on in a few papers is if you have a d-1 form symmetry. So that's when your topological operators are actually local, they're points. And it basically means that your whole theory decomposes into sectors, at least for all correlation functions built out of operators that are higher codimension than 1, everything just splits into different sectors. And so in some sense it's very boring. You just have a direct sum of things. But you can actually go, under renormalization group flow or other things, or looking at lower dimensional parts of your spacetime, there are situations where this can be interesting. And there are also situations where this can be mathematically interesting, but I don't really have time to discuss it today. For non-invertible symmetries, I'll just mention a couple. We'll be digging into more examples later, but if you have two-dimensional critical icing, the Kramers-Vannier duality defect, so when you cross it, it implements Kramers-Vannier duality, which is a self-duality at the critical point. That's an example of a non-invertible topological defect or topological operator. And there's also a more general class of things called duality defects, rep G symmetries, which I'll talk about more later, and so on. Okay, so to focus my story because I do want to try to be systematic, I'm going to restrict to a class of quantum field theories that are a bit easier to deal with, namely two-dimensional conformal field theories. I'm not really going to be using the conformal part very much here, but it's sort of in the back of my mind because those are examples of theories that I know very well. So the basic objects that you compute here are correlation functions. And I would say historically, when if you learn two-dimensional conformal field theory, especially if you learn it from, say, a particle physics point of view, normally you learn about correlation functions that look like this. So you've got some surface, maybe some genus 2 surface like this, and you've got some point operators inserted at different points. And your theory should take this picture essentially and give you a number. And that's great, that's true. And you can, it's still a very rich structure that you can study. And if you want to do string scattering amplitudes or something, this is exactly what you want to be studying. However, as we've just learned, there are also line operators in this kind of theory. And so there are much more complicated correlation functions that you probably might want to think about in some situations. So here I've got point operators like this, but I've also got lines that wrap cycles. I've got lines that intersect other lines and end on other points. There's a much larger class of kind of observables that I might want to, again, keep in mind. So when I'm talking about the line operators in my theory, as I said, they can meet at junctions. So here I've got a bunch of n lines coming together at some junction. At that junction, there will be some Hilbert space worth of operators I can put there. There is a state operator correspondence as well. So this set of operators that live here will be sort of state operator equivalent to some sort of twisted states, basically states that live with a defect inserted in space. But yeah, that's the general story. Now, if I'm restricting to topological lines, then there's a special class of operators I can put at these junctions where the junction operators themselves are also topological. So in that case, so if the lines are topological, it means I can wiggle them around. But normally you might have to put some kind of heavy object here, and so then that part is anchored. But if you're lucky, then you might find that there are some sort of weight 0 objects you could put at that junction, and then you can move the whole junction around as well without changing the value of any correlation function it's in. In the case of group-like symmetries, it turns out that the condition is that the product of the group elements, as you go around this, all the lines around this junction, should equal the identity. If that's true, then there exists a one-dimensional space of topological operators you could put at the junction, and if it's not true, then not. Okay, so these junction operators, they're a little bit unfamiliar, but you should really treat them very much the way you do ordinary point operators in some conformal field theory. These operators really you should be thinking, just like you're in a lab or something. I want to measure temperature at this point in space at this point in time. That's a point operator. So similarly, these things live in these correlation functions. Like the sort of purely local bulk operators, I can do OBEs where I shrink one of these lines and bring these two operators together. So there should be some way of rewriting any correlation function that's got a subdiagram like this into a correlation function, a sum of correlation functions that's got a subdiagram like this. I'm being quite schematic here. Similarly, and this is important, this is quite important. So if I take topological operators with topological junctions, then similarly, it turns out I can rewrite a picture like this in terms of a picture like this, or maybe a sum of pictures like this, weighted with some phases. So in the group-like case, it's just a picture like this where I've got group elements, G1, G2, G3, G4. This diagram will just be some phase times this diagram. In the non-invertible case, there will actually be a sum there that I didn't write. Okay, so what I really want to do is to be able to talk about gauging. So what does gauging a symmetry mean? It means basically you want to do two steps. You want to first couple your symmetry to a background gauge field. I'll have to tell you what that means. And then 2, you want to make that guy dynamical. So you want to do some sum over background field configuration, some path integral. So for a discrete group-like symmetry, what does it mean to turn on a background gauge field? Basically, it means describing in some consistent way, which I'm not going to make very precise here, sort of what symmetry transformations you perform as you move around in space-time. So you break your space-time up into patches, and as you go from patch to patch, how do you sort of transform all your fields? So mathematically, that's essentially called choosing a principal bundle over your space-time, and then your charged fields are sections of some associated bundles. But just heuristically, it's just saying, okay, as I move around in space-time, how am I acting with my symmetry? That's giving the information of a background gauge field for a discrete symmetry. In the language of these topological lines, I can kind of, roughly speaking, imagine just putting lines on the boundaries between my patches. And then every time I go from a patch to patch, I cross a line, and the label of that line tells me how I should act on my fields. So, I definitely haven't done anything remotely rigorous here, but maybe I've made it plausible that the information of a background gauge field configuration is essentially the same information that is encoded in a network of these lines. So if I want to gauge my symmetry, that means I should sum over background gauge field configurations, which means summing over networks of lines. In fact, I want to do it over kind of topological equivalence classes of networks of lines. And so we see one place where things have a problem. So I should have said explicitly in this picture down here, if you have non-trivial phases in this kind of picture, that's what we would call an anomaly for the symmetry. Because now, if I have a non-trivial phase here and I try to sum over all possible networks of lines, then a network that's got this subdiagram and a network that's got this subdiagram would, in a correlation function, everything else will be the same except they'll be related by a phase. And if that phase is not trivial, then they're going to cancel. And so when I do the path integral, when I do the sum over networks, I'll just get 0, which is not a very interesting answer. So anomaly does what it's supposed to do, basically prevents you from gauging that symmetry. So if you don't have an anomaly, if those phases are 1, there's still some choices in how you weight this sum over networks. Namely, you'll get these junctions, topological junctions. You have to decide what operator to put there. Typically, your topological junction might only have a one-dimensional vector space of topological operators you could put there, but that's still a choice of some complex number. So how you weight those junctions in your sum, that's a choice you can make. And it turns out that the physically distinct set of choices give different gaugings, and that's called discrete torsion in this context. So all of this has now been formulated in a way that should work as well for non-invertible symmetries as it does for ordinary group-like symmetries. So I want to be a little bit more precise here. So to implement the sum over networks, what I'm going to do instead of kind of summing over all possible configurations of lines, I'm going to say I'm going to build this one line, which is formally a sum of, say, all the elements of my group. And I'm just going to insert that one line on all the topologically non-trivial cycles in my correlation function. That's equivalent to sort of inserting, a sum over all allowed group elements on all those cycles. And so just inserting this A everywhere accomplishes the sum over networks that I want to do. So this A is called a topological, or it's called an algebra object. And I have to be careful here. I also have to specify what to put at the junctions when I've got 3 A lines coming together. So some operator at each of these junctions, I'm going to call that guy mu. If I specify A and mu, that's equivalent to specifying a gauging. So the discrete torsion, for instance, would live inside of mu. And there's some consistency that needs to work, be true for this sort of thing to work. So for instance, again, kind of like the anomaly, this picture has to be equivalent to this picture. So I have to choose an A and a mu so that that's true. So for the group-like case, it basically means that my A has to correspond to a non-anomalous subgroup of my symmetry. Okay. So it turns out that if you start with a non-anomalous group G and you gauge the whole group, it can be shown that the symmetries of the gauged theory are given by something called rep G. So in rep G, your lines are now labeled by representations of your group. Your junctions are labeled by, if you've got lines, say R1, R2, R3 for different representations, your junctions, your topological junctions are labeled by invariant vectors in the tensor product of those representations. So there's a nice mathematical structure. There are phases in these diagrams. Even if G was not anomalous, when you do rep G, you'll get non-trivial phases here, but they're computable. Fusion is just the ordinary tensor product of representations. And let me also introduce at this point, so typically we're looking at sort of sets of symmetries where there's some basic symmetries that you can build everything else out of sums of them. So in the group-like case, it was the elements of the group. Here it'll be the irreducible representations of G. So any other representation can be a direct sum of the so-called irreducible representations. So as an example, the smallest non-abelian group, S3, has 3 irreducible representations. There's the trivial representation, which I call 1 here. There's the sign representation, which assigns a -1 to odd permutations and a +1 to even permutations. That's what I call X. Tensor product of 2 copies of the sign representation gives the trivial one. And then there's a 2-dimensional representation, the symmetries of an equilateral triangle in the plane. And those representations obey, under tensor product, they obey things like this. If my group was abelian, it turns out that rep G is just essentially isomorphic to G. So I'm giving you a non-abelian example here to get something that has non-invertible lines. This Y would be an example of what we call these non-invertible symmetry. It turns out that the gaugings of rep G are in one-to-one correspondence with the gaugings of G. And so in the work I did with Eric Sharp, his student Alonso Perez-Lona, my former student Thomas van der Mullen, and Eric's postdoc Xingyang Yu, we gave an explicit recipe for computing the algebra objects and mu for all of the gaugings of rep G, corresponding to the different gaugings of G, which were just subgroups of G essentially, plus choices of discrete torsion. So in general, after you gauge, you'd like to know what the symmetries you'll get are. So I told you if you gauge all of G, you'll get rep G. It turns out if there's a sense in which you can kind of gauge all of rep G and get back to G. In between, it can be kind of complicated. And so we don't actually have a good algorithm for doing this. There are recipes for how to do it, but we don't have anything quite as explicit and easy to work with as we'd like, so we're still working on that. But essentially, you take any line in your parent theory that kind of obeys nice properties with A like this, and same thing on the other side. And that tells you those descend to the symmetry lines in your orbifold. Let me just quickly go through an example. If G is the cyclic group of order 4 with no anomaly, so the example I have in mind specifically is a free boson, radius r. You can do a translation a quarter of the way around that circle where the boson lives, the translation by pi r over 2. So that symmetry has 3 subgroups. There's a trivial subgroup where you don't do anything, you stay where you are. There's gauging the whole Z4 subgroup. So that means I'm saying I'm identifying a point on the circle with a point a quarter of the way around the circle, and that's the same as if I just had a circle that was a quarter of the radius. Or I can do the Z2 subgroup, which takes me to a circle with half the radius. Here, the residual symmetries, if I don't do anything, of course, I've still got the Z4 I have. If I do the whole Z4, I told you you get rep Z4, but Z4 is abelian, so that's the same as Z4. If you do the Z2 subgroup, though, it turns out that the residual symmetry you're left with is actually Z2 cross Z2 with some mixed anomaly between them. And in the boson example, you can see this because you should be able to go from that middle point, R over 2. You should be able to gauge these residual symmetries to get back to either R or R over 4. And that's clearly either gauging an ordinary translation or a dual translation in the language of the CFT. And we know there's a mixed anomaly between those guys. So you can get interesting structure even at these simple sizes. I'm running a bit low on time, so I'm going to go kind of quick here. But basically what we wanted to do, one of the things we wanted to do is have a very explicit formula for the orbifold partition function. So orbifold here, I don't think I used the word so far, but historically that's what we've called gauging discrete symmetries in 2D CFTs. It's called orbifolding. And there was this nice formula long known to give the partition function of the orbifold theory. So here it's sort of obvious what we have to do. In order to give it an analogous formula for non-invertible symmetries, well, we need to define what these basic building blocks are. So now it's not enough to just say I've got G and H, because when you resolve that 4-valent vertex into 2 trivalent vertices, there's actually, in principle, multiple things that could go between them. You actually have to specify some Z ABCs. You have to pick some basis of your topological operators at each of these junctions. And so given a choice of basis, you're just computing this correlation function. That's what I'm going to call Z ABC. And in our paper, we then gave an explicit formula for the orbifold partition function built out of those ingredients. You just have to expand your mu's, your junction operators for your algebra object in terms of the basis you defined. So we can now do this quite explicitly. I'm just going to very quickly mention an example, again, from the free boson. I sometimes like to joke that you can tell a lot about a string theorist by what their favorite two-dimensional conformal field theory is. There's minimal model people, and there's WZW model people, and so on. I'm definitely the free boson. That's my favorite. So in the free boson, there is one point, the self-dual radius, where the symmetry gets enhanced, and you have lots of interesting symmetries. For instance, A4, the alternating group of 12 elements. This was long known, so if you gauge that A4, you get to one of these exceptional theories, one of the Ginzburg archipelago. But you can also gauge any of the subgroups of A4, and you land at any of these other 3 points, the free boson at radius 2 or 3, or the orbifold theory at radius 2. So using our formulas and our work, we can figure out, well, you can do this explicitly, but you can also do explicitly how you get there from the exceptional theory. So here there's a rep A4 symmetry, and you can gauge any of these guys. So one interesting thing is that it turns out, because there were 2 ways of getting to the exceptional guy here, turned out that gauging A4 or A4 with discrete torsion both give the same theory. There's 2 guys here. That leads to an extra defect you can construct called a duality defect. And then similarly, by computing the symmetries you get over here, you find that there should be a rep A4 symmetry at R equals 3. And that was something that hadn't been predicted at that point either. All right, so just looking forward, we want to do some more work exploring decomposition and resolution of anomalies by these non-invertible symmetries. More detailed exploration of the C equals 1 moduli space. Discussion of symmetry enhancement, I think, is an interesting topic to cover. And then more of a systematic exploration of non-invertible symmetries for other classes of CFTs. Those are some of the things I'm thinking about. Thank you very much.
Questions for Daniel?
There's some non-invertible symmetries that don't come from any known group or stuff like that.
That's right, yes.
Fibonacci stuff. Do you have any insight on those?
Yeah, well, so most of our explicit work was on rep G, but so for instance here, where we found there was an extra gauging that kept you at this point. So there's this construction, which I didn't talk about, called the duality defect. So you can do that here and build a duality defect. So that's one of these guys. Once you add the duality defect in, it's not rep G. Well, actually, it turns out it is a rep G, but not the same G. And so that's an interesting extra structure here. So the basic ideas we can implement even for these more general categories. But sort of the explicit results we focused on the rep G case.
Yeah, so I was going to ask precisely what one learned about this famous picture from Ginsburg et al. From the 80s. And I guess what you're telling me is that there was a non-obvious rep A4 symmetry at R equals 3.
That's right. That's the main sort of new thing we learned
Right.
here.
Because, I mean, most of what you told us, dates back to non-abelian orbifolds from
That's right.
Stone Age,
That's right.
Most of the things
Indeed,
are just,
indeed.
a rephrasing of stuff
Indeed,
there.
indeed.
But this sounds like something genuine.
That's right. So in fact, there had already been identified an extra non-invertible guy here because you can, again, do a duality defect construction. If you do a Z9 orbifold, you get to the radius 1/3, which is the same as the radius 3. And that builds some extra defects here. But it turns out that the fact that there's also a rep A4 means there's got to be yet another duality defect there, or yet another non-invertible defect there that's not just that guy plus invertible guys. And so there's some bigger structure. I think at least I don't know what the full structure of the symmetries there is. I'm amazed that even the free boson is still got some surprises for us here. Yeah.
Okay, so let's thank Daniel again.
you.